In continuation with our lecture of qualitative analysis, we have already confirmed the presence of carbonate ions in the mixture by the wet tests in terms of soda extract being taken and carbon dioxide being evolved as the equations which have been mentioned. And this is how the figure goes, wherein calcium carbonate is being formed, causing milkiness in lime water, and if carbon dioxide is passed for a longer time through this calcium carbonate, then the milkiness disappears due to the formation of soluble calcium bicarbonate. Moving on to the confirmatory test for anions. The next anion which we need to detect in a mixture after carbonate is sulfide. For this, 1 ml of the soda extract is taken in a semi-micro test tube and 1 ml of sodium nitroprusside solution is added to it. Once the observation is seen as a purple coloration which is observed in the solution, it confirms the presence of sulfide ions in the mixture, and this is what the equation says. Sulfide ions reacting with sodium nitroprusside given as Na2FeCN5NO giving Na4FeCN5NOS, which is the composition of the purple color as in case of the detection of sulfide ions. The next ions which need to be discussed are sulfite ions, SO3 negative. Test which is performed is where 1 ml of soda extract is taken in a semi-micro test tube. Few drops of dilute HCl are added to it to neutralize it. Since this soda extract is alkaline in nature and certain tests which needs to be performed are in neutral solutions, so dilute HCl is added, very dilute acid is added to it to neutralize it, and then 1 ml of barium chloride solution is added. The acid which is chosen for neutralization is in accordance with the common ion of the reagent which has to be further added. For example, in this case barium chloride is added and the acid which is chosen to neutralize the soda extract is dilute HCl, since chloride is in common with both HCl and barium chloride. The observation which is seen is the white precipitates which are soluble in dilute HCl. These precipitates reappear on adding dilute nitric acid, and this confirms the presence of sulfite ions in the mixture. And the chemistry involved is seen as sulfite ions reacting with barium chloride giving barium sulfite which is forming the white precipitate, and barium sulfite is further reacting with HCl and the precipitates are dissolving giving barium chloride back again. The next ion which we need to discuss or as in analysis is sulfate, SO4 negative. To 1 ml of the soda extract, few drops of dilute HCl are added to neutralize it, and then 1 ml barium chloride solution is added. The test for sulfate and sulfite is the same. A small bit of difference in the observation. White precipitates insoluble in dilute HCl confirms the presence of sulfate ions. As in case of sulfite ions, the white precipitates were soluble, whereas in dilute HCl, whereas in case of sulfate, the white precipitates are insoluble in dilute HCl. And as the chemistry involved is observed, sulfate ions are reacting with barium chloride to give barium sulfate, which is a white precipitate, and gives no reaction with dilute HCl, insoluble in dilute HCl. The next ion which needs to be detected following a systematic analysis is thiosulfate. So to 1 ml of soda extract, dilute nitric acid is added to neutralize it, and then 0.5 ml of silver nitrate solution is added. Again, as we can see, the ions in silver nitrate and nitric acid are common, that is the nitrate ion is common. So the acid which is chosen to neutralize the soda extract is in common with the reagent further added or termed as the precipitating reagent. The observations include white precipitates which turn yellow, then brown and finally black. there is a gradual change in the color of the precipitate. This confirms the presence of thiosulfate ions in the mixture. And the reaction or the chemistry involved is thiosulfate reacting with silver nitrate, giving first silver thiosulfate, which is first white in color, gradually on keeping turns yellow, and on further keeping the precipitates turn black due to the formation of silver sulfide. The further ion is the nitrite ion following the systematic analysis. For the analysis or detection of this ion, 1 ml of soda extract is neutralized with dilute acetic acid. Then a tiny crystal of thiourea is added to it. Now for the neutralization of the soda extract, in this case, acetic acid is used as the neutralizing agent or neutralizing acid, since thiourea, which has to be further added, is decomposed in the presence of any mineral acid. So HCl or sulfuric acid here cannot be used as a neutralizing acid for soda extract. Only dilute acetic acid has to be used. This is then warmed, and then 1 drop of ferric chloride solution is added to it. In the observation, if a blood red coloration is observed, this confirms the presence of nitrite ions in the mixture. And the equation or the chemistry involved goes as follows. The thiourea on reaction with nitrite ions produces HCNS, which is hydrogen thiocyanate gas. This on reaction with ferric chloride produces ferric thiocyanate, which is giving a blood red coloration in the solution. Following the systematic analysis, the next ion which needs to be detected after nitrite is nitrate, which has the formula NO3 negative. So to 1 ml of the soda extract, acetic acid is added to neutralize it. Then this test is done as for nitrite using zinc dust. That means the same test which we have done for nitrite over here using thiourea is performed for nitrate, but by adding zinc dust first, because zinc dust reduces nitrate to nitrite, and then nitrite is further analyzed as the previous test where a crystal of thiourea and ferric chloride is added, which gives a blood red coloration. Now this zinc dust test is to be performed if nitrite is observed as absent earlier in the mixture. That means the indicatory test for nitrite has been considered to be negative or absent, and this zinc dust test can be performed for the detection of nitrate ions only in that case. So observation red coloration now shows presence of nitrate ions as in case of the test of nitrite. So this is how the chemistry involved is to be discussed, that is the nitrate ions react with the zinc dust, which leads to the reduction of nitrate to nitrite, and further to this thiourea is added and ferric chloride is added, which gives the blood red coloration as in continuation with the test for nitrite. Another test for nitrate ions which confirms the presence of nitrate ions in the mixture is the brown ring test. To perform this, 0.5 ml of the soda extract is taken. To this, 0.5 ml of sulfuric acid is added to neutralize it. Again, in this case, sulfuric acid is added in the dilute form, because dilute acids are enough strength for neutralization of the soda extract. Then after this, freshly prepared ferrous sulfate solution is added to it. This solution is then shaken, the test tube rather containing the solution is shaken, and then concentrated sulfuric acid is added to this by the walls of the test tube, the semi-micro test tube, and as you can see, a brown ring develops at the junction of the liquids, which is evident from the picture. So observation, as you can see over here in the picture, again the appearance of a brown ring at the junction of the two layers confirms the presence of nitrate ions, and the chemistry involved wherein the nitrate ions react with ferrous sulfate in the presence of sulfuric acid to give FeNOSO4, which is the brown ring, and which is the composition of the brown ring, and along with the byproducts which include water, oxygen and sodium bisulfite. This test, which has been just discussed for nitrate ions, is interfered by the presence of nitrite ions, which gives a brown solution instead of a brown ring, as we have seen for nitrate. Nitrite gives a brown solution, and bromide ions also interfere in the test, which gives a light brown ring. Hence, in the presence of these ions, nitrate is confirmed by the zinc dust test, which we have already discussed earlier. Next, coming to the aluminium powder test, which confirms nitrate or nitrite in the presence of bromide or iodide. Now, the thing is, question arises is, why do we need to confirm nitrate and nitrite in presence of bromide and iodide? Because all these ions give colored fumes in presence of dilute or concentrated sulfuric acid, and these colored fumes can interfere with each other. Although the color of iodide fumes, that is giving iodine, is violet, but it may tend to interfere in the brown fumes of nitrate or nitrite or bromide tests. So, to distinguish them, the aluminium powder test is performed. In this, to 1 ml of the soda extract, 1 ml of NaOH or sodium hydroxide is added, and this solution is heated. Now, if ammonium ions are present, then this heating decomposes the ammonium ions. After that, some aluminium powder is added to it, and the solution is heated again. If the smell of ammonia is observed here, it confirms nitrate or nitrite in the mixture in presence of bromide or iodide. That means aluminium powder test is distinguishing nitrate or nitrite in presence of bromide or iodide. So, the smell of ammonia confirms either nitrate or nitrite, and the brown fumes which we have got an indication earlier are due to nitrate or nitrite and not due to bromide or iodide, as in this case. Coming to the systematic test again for the next ion, which is the oxalate ion in a mixture. For this, 1 ml of the soda extract is neutralized with dilute acetic acid. Again, because oxalate decomposes in the presence of mineral acid, so acetic acid is used for the neutralization of the soda extract. After that, calcium chloride solution around again 1 ml is added to it, and the test tube is shaken. In the observations, if white precipitates formed, which indicate the presence of oxalate ions in the mixture. This precipitate is dissolved in dilute sulfuric acid, and then few drops of dilute KMnO4 or potassium permanganate solution is added to it, and we all know the color of potassium permanganate is pink. So, if the pink color of KMnO4 discharges or the color changes from pink to colorless, then oxalate ion is confirmed in the mixture. The chemistry involved for this is as shown, wherein oxalate ions react with calcium chloride, as we have just discussed, that soda extract which is containing calcium, which is containing oxalate is treated with calcium chloride, and a white precipitate is formed due to the formation of calcium oxalate. This calcium oxalate is first dissolved in dilute sulfuric acid, and then to this dilute KMnO4 is added. The oxalate ions react with KMnO4 to form manganese 2 plus ions, and carbon dioxide and water is also produced. Carbon dioxide and water is produced from the oxidation of oxalate ions, and as we all know, the color of KMnO4, which is pink, is due to the +7 oxidation state of manganese, and from +7 the oxidation state changes to +2, which is colorless, and hence we observe that the color of KMnO4 gets discharged in the presence of oxalate ions. Coming to the next ion, which is chloride, as in the systematic analysis after oxalate, chloride is analyzed, wherein 1 ml of the soda extract is taken and to this dilute nitric acid is added to neutralize it. After that, silver nitrate solution is added again around 1 ml. The precipitating reagents which are added to the soda extract are in equal quantities as the soda extract, right. So, if 1 ml of soda extract is there, then 1 ml of silver nitrate, which is the precipitating agent, is added after neutralization of the soda extract. In the observation, a curdy white precipitate which is soluble in ammonia conforms chloride ion in the mixture, and the chemistry involved which goes as follows. Chloride ions which are present in the mixture, they react with silver nitrate to form silver chloride, which is giving a white precipitate. This silver chloride along with ammonia, or as we say ammonium hydroxide, dissolves in it to give silver amine complex, which is having the composition AgNH3 whole twice Cl, wherein we see that the white precipitates of silver chloride have dissolved in ammonia to form the silver amine complex. Another test which can be performed for the conformation of chloride ions in the mixture is the chromyl chloride test. In this case, 0.2 gram of the dry mixture is heated along with 0.2 gram of solid potassium dichromate. After that, 1 ml of concentrated sulfuric acid is added to the semi-micro test tube. If there is an evolution of orange-red vapors, then these orange-red vapors are of chromyl chloride, which confirm the presence of chloride ions in the mixture. And as it can be seen in the picture, there is the presence of or evolution of orange-red vapors on the addition of potassium dichromate and dilute concentrated sulfuric acid to the dry mixture. The vapors which are observed are of chromyl chloride. Now, when these vapors are passed through dilute sodium hydroxide solution, the solution of sodium hydroxide turns yellow due to the formation of sodium chromate, and upon adding around 0.5 ml of lead acetate solution to the sodium chromate, a yellow precipitate is observed which is of lead chromate, and the chemistry involved in the reactions discussed are seen over here, wherein chloride reacts with sulfuric acid and potassium dichromate to produce the orange-red vapors of chromyl chloride having the formula CrO2Cl2. These orange-red vapors which are passed through NaOH give a yellow solution of Na2CrO4, which is sodium chromate. To this yellow solution, if lead acetate is added, as in the third reaction, then yellow precipitates of lead chromate are observed, and all these three confirm the presence of chloride ions in a particular mixture. After chloride, we come to the next halogen or halide, which is bromide, which needs to be analyzed after chloride. For this, 1 ml of soda extract is neutralized with few drops again of dilute nitric acid, and 0.5 ml of silver nitrate, which is the precipitating agent, is added. The test is the same as that of chloride, which we have recently discussed. If upon this yellow precipitates which are sparingly soluble in ammonia are observed, it confirms the presence of bromide ions in the mixture, and the chemistry involved is as follows, where bromide ions react with silver nitrate to form silver bromide, which is the yellow precipitate, and of course nitrate ions. Another test which can be performed for the detection or confirmation of bromide ions is 1 ml of soda extract is acidified with dilute nitric acid. To this, around 0.5 ml of carbon tetrachloride is added, and after that chlorine water or very dilute solution of potassium permanganate is added dropwise, and the test tube or the semi-micro test tube is shaken. If a brown color is observed in the organic layer, then this confirms bromide ions in the mixture. Now, the organic layer will be the bottom layer, since CCl4 is heavier obviously than the aqueous layer, so it will be at the bottom of the test tube, below the aqueous layer, and if a brown color is observed in that layer, then it is due to bromide ions in the mixture, because bromide reacts with chlorine. Chlorine water is behaving as an oxidizing agent which converts bromide to bromine, and this bromine, which is non-polar, it dissolves in the organic layer to give a brown color in the layer, and hence confirms that bromide is present in the mixture. Now this is a picture which is showing the various color of the precipitates of silver chloride, which is the first one, which is the white curdy precipitate, the first test tube to the extreme left. The center test tube of the first picture is showing the pale yellow precipitates of silver bromide, and the third test tube with the first picture is showing the yellow precipitates of silver iodide. And in the second picture one can see the layer test, wherein in the organic layer brown color is observed, which confirms the presence of bromide ions in the mixture. So after confirming chloride and bromide, we next come to the confirmatory test for iodide ions in the mixture. So to 1 ml of soda extract, dilute nitric acid is added to neutralize it. Again, neutralization is to be done by addition of the acid drop wise. On addition of 1 drop of nitric acid, the test tube is shaken and whatever bubbles are there, they are to be removed. And then this procedure is to be repeated till all the bubbles are removed from the solution. And this tells us that the soda extract has been neutralized. Then after this, to this particular test tube, we add 1 ml of silver nitrate solution. In the observation, we see yellow precipitates which are insoluble in ammonia, and hence confirm the presence of iodide ions in the mixture, and the yellow precipitates are as one seen in the picture, first picture extreme right. So the chemistry involved, which is iodide ions reacting with silver nitrate, giving silver iodide and nitrate ions, and silver iodide are the ones which are giving a yellow precipitate in this test tube. Another confirmatory test which can be performed for the detection of iodide in the mixture is that 1 ml of the soda extract is neutralized again with dilute nitric acid, and to this 0.5 ml of carbon tetrachloride is added, and after that chlorine water is added or dilute KMnO4 is added. The role of chlorine water and dilute KMnO4 is the same. They both are behaving as oxidizing agents, and they are oxidizing the halide into the halogen, and by that the halogen is getting soluble in the organic layer. Then in the observation, a violet color in the organic layer confirms iodide ions in the mixture, and this is the chemistry involved, wherein iodide reacts with chlorine water or KMnO4, very dilute KMnO4, which performs the same action, giving iodine and chloride, and this iodine dissolves in the CCl4 layer to impart a violet color to the CCl4 layer. The next science which we move on to is the detection of sulfate ions, or rather confirmation of sulfate ions after its detection in the mixture. For this, 1 ml of the soda extract is neutralized with dilute HCl, and then around 1 ml of the barium chloride solution is added to it. If a white precipitate is obtained which is insoluble in concentrated HCl, it confirms the presence of sulfate ions in the mixture, and the chemistry involved can be seen as sulfate ions reacting with barium chloride to give barium sulfate, which is a white precipitate, and this white precipitate is insoluble in dilute HCl. Another test which can be performed for the confirmation of sulfate ions in the mixture is 1 ml of the soda extract is taken, and to this few drops of dilute acetic acid are added, and after that 1 ml of lead acetate solution is added. Again, for neutralization, as you can see, dilute acetic acid is added because it contains the ion in common to the precipitating agent which we are adding afterwards, which is lead acetate. So the chemistry involved is as follows, where sulfate ions react with lead acetate to produce lead sulfate. Lead sulfate is a white precipitate, and this lead sulfate on further action with ammonium acetate gives lead acetate, that is lead sulfate gets dissolved in ammonium acetate to produce lead acetate and ammonium sulfate. The next sign which needs to be detected here is phosphate. We do not have any kind of indicatory test for phosphate. The only test for phosphate which needs to be performed is a confirmatory test, and this test is to be performed with either the soda extract or it can be performed directly with the mixture also. So, if you have to perform this test with the soda extract, then to 1 ml of the soda extract, dilute nitric acid is added to acidify it or neutralize it. This is then heated and a drop of concentrated nitric acid is added to it along with ammonium molybdate solution. If canary yellow precipitates are observed, it indicates the presence of phosphate ions in the mixture. So, phosphate ions, as you can see the chemistry involved, phosphate ions react with ammonium molybdate NH4 whole twice MoO4 plus nitric acid. It gives yellow precipitates. Canary yellow means a very bright yellow color of phosphoammonium molybdate, whose formula you can see on the screen. This test can be performed directly with the solid mixture also, and arsenate ions interfere in this test. That means they give a similar kind of a canary yellow precipitate of ammonium arsenomolybdate. So, for that, to distinguish between arsenic and phosphate, separate tests are there which we will discuss later. Another test which can be performed for the ions like fluoride and borate. These tests can be performed directly with the mixture. For borate ions in a mixture, a pinch of the mixture is taken and 1 ml of ethanol or ethyl alcohol is added to it in a semi-micro test tube. Then concentrated sulfuric acid is added, the semi-micro test tube is heated, and the vapors which come out of the test tube are burnt in a flame. As you can see the picture, the flame gives a green edge. This is the observation. A green edged flame confirms the presence of borate ions in the mixture, and this is the chemistry involved, wherein borate reacts with ethanol and sulfuric acid to produce triethyl borate, which is highly volatile and gives a green color or a green edge to the flame. And for fluoride, the test which is performed directly with the mixture, where the mixture is taken in a semi-micro test tube and a little of sand or silica is added to it. After that, concentrated sulfuric acid is added and the semi-micro test tube is heated, and a moistened glass rod is kept on the mouth of the test tube from where the vapors are coming upon heating. If oily droplets are seen on the test tube and a white deposit on the glass rod, it confirms the presence of fluoride ions, and which can be evident from the chemistry over here, wherein fluoride ions react with silica or sand in the presence of sulfuric acid to form silicic acid, and further gives SiF4 with water, or on the moistened glass rod SiF4 white precipitates are observed. So, this is all for today. Thank you so much.